try to prove this inequality today. It's a fairly barren looking inequality, but if you'll notice, things look pretty close here. This number on this side is less than, square root of 222 is certainly less than the square root of 225. And I picked 225 because it's a perfect square. It is 15 squared. So this is 225 square root of 225, which is equal to 15 squared. So this is just equal to 15. And so you can see why this is interesting. This is 15 right here. You have 5 here. You have a number that's less than 5 here, the square root of 22. Then you have a number that's greater than 5. So greater than 5, equal to 5, and less than 5. All right. So it's kind of up in the air if this is really true or not. So I mean, it looks like it's going to be kind of close. So let's see where this leads us. Now let's move along to the next screen here. Let me get my marker. Okay. Okay, folks. Now the result that I chose to use to actually prove this is something called the Cauchy-Schwarz, and that's this object right here. And if you've dealt with vectors, this is like the magnitude of a vector squared, this is the dot product squared is less or equal to the magnitude squared, I think. So it is related to vectors. And equality holds when the vectors are multiples of each other. But right now we can just treat it as real numbers. Now, so what I want to do here is introduce this idea called the one trick. What you can do, since this is something that holds for all, it holds for all sequences of a sub I and b sub I, the notation we're using here, the subscripted notation, that are real numbers. Okay, so it holds, I think it also holds for complex numbers, but that's another video, I guess. So in other words, this holds for all real numbers, which means that you can pick whatever you want. And what I chose to pick was a sub I equals 1 here. Now this is well known. It's called the one trick because, again, you have carte blanche to select whatever variable suits your fancy. Okay, and so we're going to pick the a sub i's to be equal to 1. All right. Now notice in this case, we have 3 summands over here, so that would correspond to n equaling 3 here. Okay, n equal 3. Now I discarded the summation notation and just wrote it down like this. So notice the a sub i's, I equals 1 to 3. Your a sub i's are always equal to 1. And for emphasis, I put the hard-coded 1 right there. 1, 1, and 1. And of course, b sub 1 is root 27, b sub 2 is 5, and b sub 3 is root 22. And the rest of it is just a straight handoff to this left-hand side. Okay, to this to this right-hand side. So again, it seems superfluous, but I wrote 1 squared just to let you know where everything is coming from. Then here I wrote the square root of 27 squared, 5 squared, and the square root of 22 squared. Okay, well, this would be 27 plus 25 is 52, plus 22 is the 74 you see on the right-hand side here. And then these guys right here add up to 3. That's equal to 222. And if you take the square root, that proves the inequality. That proves exactly what we set out to prove. We took the square root of this, which is what we were trying to verify up here. So the result has been proven. Now notice here a little subtlety here. This says less than or equal to. Equality holds here, I believe, and I'm a little rusty on this. Equality holds if your a sub I, if they're proportional, and I'll just write it out. If a sub I over b sub I, okay, that's supposed to read a sub I, the quotient of a sub I and b sub I. If that's equal to the same constant all the way through, then equality would prevail, all right? But that's not the case here because this is kind of trivial here, but you would just have root 27 equals to 5, which it doesn't. I mean, you see the way I've got it set up here, let's see, I did the a sub i's as the 1s, but you would have 1 over root 27 plus 1 over 5 plus 1 over root 22, where they're not going to equal to the same constant, right? That's kind of trivial. But anyway, so that means the equality does hold, the inequality does hold, the equals part holds if you have this going on, but we don't have this going on. We don't have I guess you would call this proportional, okay, that these coordinates are proportional. So that's why we have the strict inequality here. And y'all, this is very, very close. I did the decimal, but I didn't go to the trouble to write it down. But it's super, super sharp. You know, it's very, very, very close. I think within thousandths.